All right, hello and welcome. Today is Friday, April 24th. It's our day 5 of our review series for AP Physics C. We've been, we've been talking about all the mechanics topics, of course, and then we'll move on to our E&M stuff. You know that you have a mechanics homework that is due next week, so make sure you go to your My AP and then continue to work on your My AP homework as well as the video thing. So don't forget about the video project. Here's a quick video so that you remember about the video project. Now this is a YouTube channel. These guys are pretty well known. It's called Dude Perfect, and they do all sorts of sports related trick shots and other things. I mean, they have millions of subscribers and stuff. They're pretty well known. They also they're smart in that they brand and merchandise. But anyway, besides all the business talk, they have a huge series with ping pong balls. This is the Ping Pong Trick Shots 3, and let's see what they have.
This is the ricochet shot. What a shot!
Now, typically in their videos, it looks like they are literally one-shotting everything, right? I'm sure that they've taken multiple takes and videos, and they just cut the video and take the one that actually works. Nishek will be in purgatory for a long time for what he did. Wait, what happened? Your internet is... yeah, we're gonna actually do that problem right now, so don't worry. I asked to leave the comments below, and zero of, so that means no one actually knew how to solve it, or you just pulled the senior card and getting super senioritis. But anyway, so that's Dude Perfect. So they make cool trick shots. As you can see, they use little wooden boards to ricochet the ping pong ball off. So gentle reminder, it's a great way to get extra credit. All right. Yeah, So no one solved it. So let's see if we can do this quickly, and then we'll move on to our review number 5, which is on rotational dynamics. We created a sphere. So imagine playing Amazon's New World, video game, where I have no idea what you actually do, but it's kind of like Minecraft, but with better graphics, I suppose. But anyway, so you have this wooden cylinder part, or I don't know, ideally it should be wooden because you're going to make a spear. It should be easy to handle. What did we say? I think the radius was R, so we used only variables. The radius is capital R. And what was the length of the first one? The length is... Chat, you gotta stay with me. There we go. Thanks, good. It is capital H. Whereas the cone, which is made of a different material. Here, let's use different colors. I'll use this pink color. So my staff here, my wooden staff, has density. I think it was row 2. This one was 2. Yeah, so stay tuned. You're gonna learn a lot today. You know what that means. And then we have this cone, the pencil-like pointy part for our jousting rod. Yeah, that is definitely not it. The cone is little h long, or high, I should say. And of course the base radius is the same because it's part of the cylinder, right? And it has density rho 1. Okay. All right, so the goal was to find XEM, and of course each individual piece, the wooden one, and then the actual pointy end. Typically, the pointy end is probably made up of stone or whatever we can find to make it sharp and strong. So imagine being in like Survivor, or what's that book you guys have to read? Lord of the Flies. There we go. Imagine being in Lord of the Flies. All right. We want to place our spear at the origin, like so. Okay. Now each object, each material has its own center of mass. Yeah. So make sure you have a really good sphere and you know where the center of mass is, so you can handle it well, and then you'll be good. So this wooden one, now because it's nice and symmetric, it's actually easy, right? We know that the center of mass of the first, I guess technically it's the second material because they called it row 2, is directly at the center. So this is M2, and M2 is located at X2. Okay, what is M2? Well, M2 would be the mass of the entire object, and using density, which is mass per volume, then the mass must be density times the volume, and so density is rho 2. The volume is just the volume of a cylinder, which is pi r squared times the length, which is h. Right, so that's mass 2. The position of mass 2 is at the center of mass of the object, and the center of mass of the object is x2, and because it's nice and symmetric, x2 must be half the distance at h over 2. All right, now the harder part, the cone. So we want to find the center of mass of the cone and then place it so notice how the cone has a wider base, obviously, and a pointier end. Of course, in order to balance this out, it would have to be somewhere closer to the base, right? If you know your geometry, you could basically just do it straight from geometry, but we're going to use calculus to derive it. So it's also a nice review for our Calc BC kids. Hint, if you're thinking 1/3, 1/3 is for a two-dimensional object like an isosceles triangle. So if I had a two-dimensional object, then it's the 1/3 2/3 split. But for a cone, it's slightly different. And today we'll see, using calculus, we can figure out where the center of mass is. All right, now M2 is pretty simple. So let's see. Let's just the cone. Just the cone. Here we go. Yeah, it's not going well. It's not going well. All right, so we want to figure out where the center of mass is. We're going to take a bunch of slices. So if I slice this, you can see how the slice is basically a disk. Okay, if I place this on the x-axis, okay, and then we'll do a two-dimensional cross-section of our cone. This is the two-dimensional cross-section of our cone. Okay, at the base, the height of our triangle is capital R. Okay, and in this case, the length of this thing is actually the height of the cone, which is lowercase h. Lowercase h. Okay. All right. Now, the infinitesimal amount of mass, dm, must equal the density of this object, which is rho 1, times the volume. The volume of this infinitesimal slice would be pi times r squared. Okay, r is a variable, and we'll see what it is in a moment. R squared times the thickness of the slice, and the thickness of the slice is dx. Okay. Now what is r? Well, the radius when at 0, it's all of it, it's capital R, but as you can see at different positions, at different x's, it is a different value. It's the y value of this function here. So what is this function? This function is has a slope that is negative, right? It's negative capital R over H, so rise over run, but it's negative, so I should say fall over run, times X, wherever your position is in X, and plus the y-intercept, so this is slope-intercept form, plus the y-intercept, and the y-intercept is capital R. So let's go and replace our dm with this function. So dm must be equal to rho 1 times pi times negative r over h x plus r quantity squared times dx. And we want to find the center of mass of a cone, and then we'll use that again to find the whole thing later. But xcm is your mass times the distance. So we have a bunch of dm's. We're going to multiply it by x, whatever the position is, and then we'll take the integral. I should write it this way: over the sum of all the masses. Over the sum of all the masses, and the sum of all masses is m1. Okay. What's our bound? Well, we're starting from x of 0 all the way to lowercase h. From 0 to lowercase h. Okay, now let's put it all together. We want the integral from 0 to lowercase h of x times dm. So this would be rho 1 pi times negative r over x, oh no, r over h, undo, r over h times x plus r quantity squared times this other x. This other x comes from the xcm formula, times x, and then we got the dm, divided by m1. m1 is the total mass of our cone. And no, it's not. Sorry. Divided by m1. m1 being the total mass of the cone. The total mass of the cone should be the density of the cone times the total volume of the cone. Of course, the total volume of the cone is 1/3 pi r squared times h. 1/3 pi r squared h. Okay. All right, well, let's go ahead and simplify as much as we can, factor out all the constants. So, and we can actually see that the constants kind of cancel. Let's see, the rows and the pi's are all gone. I'll put the 3 above, so I'll take the 3 up because I don't like fractions in the denominator. So we have 3 in the top, integral from 0 to lowercase h, okay, of this function. What is this function? First, we have to FOIL and then multiply it by x. So if I FOIL, I get negative r over h times x times r over, so the negatives cancel out, giving me a positive value. So we get capital R squared lowercase h squared times x cubed. Why is it cubed? Because we have an extra x. Make sure you put that back in after you FOIL. Should it be dx at the top? Should it be dx? Yes, very good. Dm is blah 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 dx. So I have dm here. This should be dx. Thank you for pointing that out. Correct. Otherwise we can't. Otherwise x is a constant. We just FOIL factor it out or something, and you just get an m at the end, and nothing makes sense. All right. What's the second term? The second term is the inside and the outer. So inside gives me negative r over hx times r, so that's r squared, and then there's two of them, so minus 2 r squared over h times x squared. Again, it's x squared because we have an extra x. And then the third term is r times r, which is r squared, times x gives me r squared x. Okay, and then dx. All over r squared h. All right. Yep. Let's just go ahead and finish this off. Let's see. We got cubic, you get over 4, so r squared over h squared times x to the 4 over 4 minus 2r squared over h times x cubed over 3 plus r squared times x squared over 2 from 0 to h all over r squared h. Now from 0 to h, well, every term inside has an x, right? This one has an x, this one has an x, this one has an x. So when you plug in 0, it's going to turn to 0. The lower bound is just 0. And so all we have to do is worry about the h term. So this gives me 3 times, if x is h, so I get h to the 4th over 4, and then there's an h squared in the denominator. So I get r squared over 4 times h squared minus cube, same thing, so we get 2 over 3 r squared h squared plus r squared over 2 times h squared all over r squared h. So what is this? Well, everything is r squared h squared, r squared h squared, r squared h squared, r squared h squared. This is 1/4 minus 2/3 plus 1/2. So that's the same as 3/4 minus 2/3, which is the same as, let's see, 9 over 12 minus 8 over 12, which is 1 over 12. Okay, so I have a 3 in the front. 1/12 r squared h squared all over r squared h. All right, let's go and simplify. What do we get? No. Remember, there's a 3 in the front. One of the h's cancel, so it's definitely based on h. It is 3 over 12, which is 1/4. A quarter of the way. So for cones, different from a 2-dimensional object, this 3-dimensional cone is a 1/4, 3/4 split. All right, so that means that the center of mass is h/4 away from the end of the sphere. So when I say let's see, m1, of course m1 is rho 1 pi, sorry, 1/3, I forgot the 1/3. 1/3 pi r squared times h, that's mass 1. And where is mass 1? x1 should be, chat, where is x1? Hint, look at your origin. Where is the origin? All the way on the left side. Well, x1 is h plus a quarter of h. Okay, now that we have everything, we can finally put it together. XCM of our sphere is equal to m1 x1 plus m2 x2 divided by m1 plus m2. And so now it's just plug and chug, and we can call it a day. Let's see, m1 is 1/3, I'll write the 1/3 in the front, rho 1 pi r squared h times x1. x1 is h plus h/4 plus m2 x2 rho 2 pi r squared capital H times the distance, which is h/2. Divided by the total mass. The total mass is m1 plus m2, which is 1/3 rho 1 pi r squared lowercase h plus rho 2 pi r squared capital H. And that is the answer. Yep, I'm doing XCM for 2 points. That's how it is. Once you find the center of mass of the individual objects, they're basically like point-like particles. Okay, so what does this tell us? Well, I typically if you did build a sphere, your wooden part is pretty light in comparison to the stone part at the end. However, the stone part is usually smaller, so there is a tug of war between them. If you balance it correctly, then what you should do is, make it so that somewhere at the center of the geometric center is your overall XCM. Make it so if you design a sphere, so make it so XCM is at midpoint. Okay. Now, knowing that by doing this, knowing that the midpoint is directly there, now when you're holding your sphere, you can do all sorts of trick stuff. Where's our professional color guard, dance guard person, wherever she is? Regina would know how to like twirl this thing around, and by knowing where the center of mass is, you can kind of twirl it around and do all sorts of kung fu stuff. Oh God. All right, so what is this center of mass? Let's assume that we found our center of mass and we fashioned our sphere strategically so that it's somewhere at the geometric center, like so. The center of mass is our balancing point, is our fulcrum. If I put a fulcrum here, this leads directly into our next topic, which is torque and rotational dynamics. That means that the force on each side are balancing the the object at this fulcrum. So make sure you use these words in your explanations. The pivot point. And so torque, of course, is equal to R cross F. It's cross product, and now it is different. You know, don't say it's F cross R. That'll give you the negative torque. Remember, when you take the cross product, you point your fingers towards the first vector, R vector, and then you curl your fingers towards the second vector, in this case the force vector, and your thumb tells you the direction of the torque. Right hand rule. So let's see. Let's try the right hand rule for these two torques. So torque 1, I'll use orange. Okay, this torque 1 from force 1. Okay, so from the pivot we have our radial arm. R is always away from the center, so that's our R. So we point our fingers towards R, which is to the right, so all fingers towards the right. And then now you have to bend your fingers towards the force, which is down. So you bend your fingers down. Pointing to the right, bend your fingers down. You can see how the thumb points into the page. Okay, so this clockwise turn has a direction that is into the page. Okay, and the opposite can be said about the other one. Torque is I alpha. I alpha. And this is where we get to all of our moment of inertia stuff. Where I is the moment of inertia. Chat, what are the units for moment of inertia? What are the units? Ooh. If you just remember the formula, you can figure out what the units is. Formula is integral of r squared dm. And so we get meters squared. There you go. Meter squared times kilograms. Kilogram meter squared. Kilogram meters per second squared would be newtons. That's mass times acceleration. All right. You guys know how to derive, hopefully, derive some of them. All right. So what was new in APC? We did the parallel axis theorem. What is the parallel axis theorem? Well, parallel axis theorem tells you that if you know what the, let's say it's a rod. Pew, pew, pew. Let's do a rod. Just like your spinning rod lab. Rest in peace. What's the moment of inertia about the center of mass, ICM? Let me move this to the right so we're not confused. So this is just okay. So for rods, it is 112 ml squared. 112 ml squared, right? where L is the entire length of the rod, not the radius. See, this is why I told you to have your make a binder. Some of us might be overconfident and start making silly mistakes. I don't want you to get a 4 because you made a silly mistake. Get organized. Let's get it done. All right, so the parallel axis theorem tells you that you can find the moment of inertia about any other axis that is parallel. So parallel, that is some distance d away from the center of mass. D distance away from XCM. So the overall moment of inertia about this new axis is equal to the original ICM plus md squared. I meant R as in the reach of the rod, how far it reaches, aka length. Yeah, I don't know how many people are going to buy that, but good luck convincing the College Board that's what you meant. Now, what does this formula tell you about the moment inertia? Look at it. It tells you that if you find the moment of inertia about any other axis that is not the center of mass, the value is going to be more, right? Which means it is harder to twirl around your rod if you're away from the center. So the center is where it is the least, where the moment of inertia is the least, right? So you can try this with any object, really. So like if you have a pencil on you right now, just flip the pencil up into the air. You'll see that naturally the pencil spins around about its center of mass. You can do this with your phone. Now, phones are slightly more complex. You might get angled rotations. But there is a video of an astronaut spinning, something like that. So it'll, again, naturally spin about its axis that has the least moment of inertia. All right, perpendicular axis theorem only works, when it's nice and symmetric for a symmetric body. So don't use perpendicular axis theorem. Well, the axis that it will spin through will go through the center of mass. So whatever it's spinning around, the axis that is spinning about, that axis has to go through the center of mass. Now, the axis itself can be tilted based on the structure of the object. When did we use perpendicular axis theorem? That was for our coin, right? If we spin the coin around. So if you spin a coin, pew, pew, this is IY, this is IX, and we also have IZ. And of course we learned that IZ is equal to IX plus IY. Right? So when you roll a coin, when a coin is rolling, it's spinning about the z-axis. What is the moment of inertia of the coin? So imagine flicking a coin like a quarter along your desk as it rolls around. Okay. Remember, this is a disk, and what is a disk? Well, moment of inertia of a disk is 1/2 mr squared, right? And we can see how, based on symmetry, Ix has to equal Iy, because the axes are arbitrary, and they have to add up to 1/2, therefore it must be 1/4. Okay. Now, logically, explain why it has to be less than. It has to be less than Iz. Why does it have to be less than Iz? So if I take a look, all objects from Iz is always radially r away. So any infinitesimal mass, when I'm spinning about the z-axis, any infinitesimal mass is r distance away from the axis of rotation. But if I spin about, let's say, the y-axis, how far is the mass from the y-axis? That same mass that is little r away is now r sine theta away. And r sine theta is smaller than r. Right? So if you spin around the y-axis, each mass, each dm, each little dm is slightly closer towards the axis of rotation, and therefore the moment of inertia should be less. Okay. Speaking of rolling quarters, we can move on to rolling motion. Recall that rolling motion is equal to rotation plus translation. And when it is rolling without slipping, V equals omega. At the bottom, the velocity is, so rolling without slipping, at the bottom the velocity is 0. So this is just AP1 review stuff. The center of mass moves at V. The top moves at 2V. So this creates the cycloid shape for its position function. It's a PT graph. Right? So since V equals omega, we can say that x, which is the linear displacement, is equal to r theta. This is basically arc length formula. Omega in radians per second, theta in radians, and therefore A equals alpha. Okay, this leads us to rotational kinematics. So take a look at your Vovat stuff, then you got your Wowatt, you know, the Teenage Mutant Ninja Slugs, the rotational cousins, etc., etc. So review your AP1 stuff. If it is slipping, then V does not equal omega. Okay. All right. Question. Let's see. Let's do some AP questions. Let's say we have a PVC pipe that is rolling down a ramp. How can I test and figure out if the PVC pipe is slipping while rolling down the ramp? How do you test? just saying energy is not going to help me, right? How do you tell if, well, we basically need to see if this is true or not, right? So logically, what you do is you look at the question first, okay? Then think about what needs to be true or what needs to be false in order for you to prove something. So in order to tell if this is slipping or not, this relationship has to work. If it's equal, then we know it's not slipping. If it's not equal, then we know it is slipping. Okay? No. So what we need to do is independently measure V and omega. So find V on its own without the use of omega, and then we have to find omega on its own without the use of V. Okay, if you start using energy, you're gonna get in trouble because you got I omega squared. Okay, so this, I mean, technically, yeah, you could use energy, but eventually you'll see that in order to find Ke, you need V. In order to find Ke rot, you need omega. So might as well just find V and omega by itself, right? Instead of dealing with masses. Right. So first, we need to see what V is. V will be based on the center of mass. So as if this object was a point-like particle, okay, we have to find what the final velocity is at the bottom of the ramp after coming down the ramp of height h or whatever, of angle theta. Okay, so use Vovat. So in order to find the velocity of center of mass, that's where Vovat comes in handy. Okay. Now, in order to find omega by itself, omega would be my angular velocity. I have to see how many turns it makes, because omega is delta theta over delta t. Essentially, I can use Vovat to find omega. And so this is where, you know, you do a little marking here. So imagine at the edge of your pipe, you know how there's some sort of thickness to the pipe, of course. There's like an inner radius and outer radius. Okay. At the edge of a pipe, you put some physics tape, some blue tape, or a marking. And this marking will help you figure out if it completes a rotation or not. Yeah, so very good mystery wizard, very good. So now, by figuring out, you know, basically you have to take slow-mo vid or something. As it rolls down, you can figure out how many omega, what your omega is using Vovat. Okay, your linear distance that you travel. So when you're rolling, in one full rotation, in one revolution, how far do you move? Well, in one revolution, you are linearly moving the circumference worth of distance. Okay. So each revolution is a circumference worth of distance that is traveled. Well, at least it's supposed to be, right? But anyway, so what do? Well, we measure how many rotations we make as it's falling, and we measure how long it takes. Of course, you're starting from rest. And then based on how many rotations, how many revolutions, convert your revolutions into radians. And then you can solve for omega final. Okay. Similarly here, we start from 0. Okay. We can figure out what d is. Remember, the d would be the hypotenuse. What is the hypotenuse if the height is h? Okay. Sine of theta is equal to opposite over hypotenuse. So d is h over sine of theta. And then measure the time. And then you can find final velocity. And then after independently finding them, you see if the relationship holds true. All right, that was a cool design problem. Okay. During the energy thing, I talked about rotational energy as well, right? So here's a question that I'll leave you with. Earlier, I think it was Monday, we did a loop-de-loop negotiating problem, right? Where we lifted off a ramp at some point. It was a marble in a cup extreme version. Anyway, we'll skip the trajectory part this time and just focus on the loop-de-loop part. So imagine this thing being on the ground, of course, radius r, and we found that we found that minimum velocity occurs at root gur. Okay. Right? But this assessment that we did was for something that is actually sliding, not rolling. Okay? When you say that your pegmaga over here is equal to Ke plus peg 2 over here, you are assuming that the object is sliding. It's like a roller coaster cart. But what if, now, here's the question, what if instead we have an actual marble that rolls? So there's enough friction for it to roll. It has mass m and radius little r. And it rolls down without slipping. No more slipping stuff. Okay. How does this change the system? How fast will it go? Sword Hero. Huh. Yeah, make sure if it's only do the free one. Don't waste your money. So if it's free, then yeah, that's fine. All right, so if it's rolling, how fast will it go? How I should ask, how high does it need to be if it's rolling? Okay, so we're not sliding down the ramp, we are rolling down the ramp. We go through a circle, a loop-de-loop of radius capital R, and we want to make sure we negotiate it properly. And in order to not fall off the track, to make sure we have enough energy, how high do we need to start from? That is the question. All right, if you can solve this, go ahead and leave your answer in the comments below after I upload the YouTube video. Thanks for tuning in. I'll see you next time.